I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray that you help us to just wrap up our thinking about matrix Lie groups and just how they work. In the name of Brother Jesus. Amen. It's not entirely true. Well, I mean, I think we'll still be doing things in matrix Lie groups next time, but it's kind of the end of the road, I think, for this book at least. So we're starting with a discussion of covering groups. And by the way, of course, if it hasn't been mentioned already, we are using Brian C. Hall's Lie groups, the algebras, and representations in elementary introduction. Nothing more to say about it. It is, of course, an undergraduate book. Let's see here. Oh, covering groups. So what is a covering group? It seems like a definition is in order. So if you have G, a connected Lie group, all right, the universal covering group aka universal cover is a simply connected Lie group H. Alright, such that what? With not just a group H, it comes with a little bit of baggage here. There's the kind of baggage we like. V such that H goes to G. What do you think this should be?
The algebra.
The algebra what?
Homomorphism.
Which one is which?
The first one's Lie group, second one's the algebra.
Yes, a Lie group homomorphism. And then the second one is what?
The algebra homomorphism.
Is it a homomorphism though?
No. Iso.
In fact, isomorphism. I believe. Let's see here. Yeah, isomorphism. As you guys know, this is the time in the semester when I get extra tired, so I stop proving things. That's my excuse. It's not that the theorems are getting harder, and it would take us much longer to prove them. I mean, okay, that's actually also it. Anyway, the proofs which I skip, of course, are in pretty good detail in this book, so it's not such a horrible offense as it might be otherwise. Come on. Theorem, do it over here. Then there's a theorem. So the theorem says, this is theorem 3.10. For any connected Lie group, a universal cover exists. So you say phi, oops, I guess H phi would be, yeah.
It's 4:00 p.m.
So a universal cover exists, and if you have two universal covers, he soon explains how to, I mean, having two universal covers is kind of obnoxious, so he adds a little bit of fine print to make the universal cover unique. I think that's what he does in the next half page or so, but I'll just state the theorem as it is. If these are two universal covers of G, then they're related by an isomorphism, then there exists an isomorphism psi phi2, well, such that psi is going from h1 to h2, and psi 2 composed with psi, rather phi2 composed with psi is equal to phi1. Right. He says, since the universal cover of a connected Lie group is unique, well, up to canonical isomorphism, it is reasonable to speak of the universal cover, G tilde, comma, phi of G. So, in our way of thinking, this means that H1 and H2, same thing. Right? Because they're equal up to a Lie group homomorphism, isomorphism rather. And so the notation that you use is, so, write G tilde, comma, phi for H phi here. All right, so the G tilde is going to be the notation for the universal cover. Let's see here a little bit more. He says since little phi is an isomorphism, we can use little phi to identify G tilde with G. And so here it is in less formal terms. The universal cover of a Lie group G, all right, is the unique, simply connected group G tilde such that the Lie algebra of G tilde is equal to the Lie algebra of G. Then the covering homomorphism is defined as the unique Lie group homomorphism such that the associated Lie algebra map is the identity. Oh, that I remember from somewhere. Every once in a while, I have a spark of remembrance. I took a whole course on Lie groups, guys. And I do remember things sometimes. I should really probably find out and teach from it. But then that would make this not a 1 hour course, but a 3 hour graduate course, yeah. It probably would be bad. Okay, so the point here is, if you say G frac G is equal to frac G tilde, or so in other words, then this phi is actually the identity map. So I don't know. It's I'm getting a little bit lost in the identification stuff here, but I'm saying is if G tilde is the covering homomorphism, and if you identify the Lie algebra of G tilde with the Lie algebra of the given group G, then under that identification, the isomorphism is just the identity. Yeah, so that makes sense. But all right. Oh, examples. Yes, examples. So here's some examples for you guys. This is a Campbell Baker Hausdorff sticky note. That's behind me, not behind you. Did you figure it out yet?
Oh, the one from last week?
Yeah, where's the mistake?
Yeah.
I started working on it. I think I might have found one that we missed.
Okay, that's hopeful.
Yeah, I need to look at it some more.
That's hopeful. That's hopeful.
We need at least 2 that we missed, because one of them has to cancel out and we have to get another one. So, gotta find something.
I'm not sure if you guys are being pessimistic or optimistic.
Pessimistic.
Pessimistic. Yeah.
Yeah.
I'll allow it. Example 1. So example 2. Example 3. Example 4. Example 1 will be G equals to the circle. Example 2 will be G equals to SO3. Example 3 will be G equal to UN, unitary group. Example 4 will be G equals to SON. So in each case, we're looking for we're looking for the universal cover. All right, and that's not a fool's errand, because all of these matrix Lie groups do have, in fact, universal covers, which are also matrix Lie groups. However, I should warn you, one of the parts of the story here we're about to discover is that, in fact, not all matrix Lie groups, connected matrix Lie groups, have universal covers which are also matrix Lie groups. To prove that isn't the case, if you look in the appendix, it involves a fair slice of representation theory. So there's something that comes from the universal cover in terms of how it interacts with the representation theory. And like you can assume that there's a certain type of representation for the universal cover, and then it has to be what's called faithful, and then you can prove that the representation isn't faithful, and consequently you get that there is in fact no universal cover that's a matrix Lie group for I think like SLN, special linear group. So there is still a universal cover, it's just not a matrix Lie group. It takes you outside the world of matrix Lie groups to other things. Not every Lie group is a matrix Lie group, remember. It's just that's our world for the most part in here. So what do you guys think? The Lie algebra here is just the reals, right? It's abelian, so it's just one-dimensional Lie algebra, trivial bracket. What do you think? By the way, is the circle simply connected? And why not? Sorry. What is simple connectedness?
Well, it's got to be able to every loop in the thing straight down to a point.
Right. That's the geometric answer. Fundamental group is the identity, right?
Yeah.
If we know what the fundamental group is, but exactly that. So take a loop around the circle. You can't.
That's right. Yeah.
So yeah, it's not. So what in fact, the G tilde here is just equal to the reals. The reals. And the homomorphism is what? What's the covering homomorphism?
It's gonna be like u to the I theta. Or,
Yep.
yeah.
Yep. So, oh wait a minute, I've got it the wrong way, right? How does the covering homomorphism go?
It goes from H to G.
So I've got it,
Right, or, yeah.
I got it upside down here. So I went from R to S1, and yes, the mapping is exactly theta equals to e to the I theta. There you go. That's the covering homomorphism. I got bad news. That's the easy one. Well, I don't know if that's bad news, but it's just honest. This one. Yeah. SO3 has, let's see, what has the same Lie algebra as SO3? I don't know if we've done enough for you guys to know that, but SU2 happens to have the same Lie algebra, has the same structure constants. So in fact, it's SU2 as your G tilde. I think that the details of this are actually probably clearer in that quantum field theory book I was showing you than a lot of places. Because I remember in there it wasn't too hard to see, because Basically, any one of these things you can build from exponentiating angular momentum. Well, you can build this from exponentiating. Anyway, it's sufficient to say that the covering homomorphism here is not at all a simple. No, I don't mean that in a technical sense. I mean, how do you get from here to here? I believe this is the question which was vexing to us earlier in the semester. Remember?
Yeah.
I told you guys, oh, we'll figure out the map from here to here.
Oh, and it says it's the map described in that section. in the book.
Yes, it does. What does that section tell us? Tell me.
Well, it didn't tell us
Section-
the actual map, which is.
Oh, it doesn't. Section. It doesn't tell us the actual map. Section
That's
1.6.
why we were trying to find it.
Well, no.
That was in a.
That was in our previous naive life.
Oh, that's right. That's right.
The map may well be described in here. Maybe. He says specifically there exists a league. I think he actually has details here.
Yeah.
So he's like, look at 2x2 complex matrices which are self-adjoint and have trace 0. So let's see here. I'll try to describe the map over here. Why not? So A1, 0, 1, 1, 0. A2, 0i, minus I0. A3, 1, 0, 0, minus 1. How do these work? It says you can define an inner product. Alright, so, okay. Suppose U is an element of SU2 and A is an element of V. So what's he do next? What's his next thing here? V is what?
R3.
I think V is the span of these guys, right? And it's a real span too, isn't it?
Yeah.
Well, yeah, real vector space with the following basis. So V is space. Listen, space. I haven't used space as an operation yet. Why don't people use space as an operation? I wonder. So V is that span, and he tells us that you can make V into an honest goodness inner product space by using this, right? Maybe. If you take the product of these, what do you get?
Like for all of them.
Like with this, for example, A1 with A2, you get what? Like
Negative I, 0,
0.
0,
I.
I. Yeah.
right, so we get minus this, right?
No.
Would be minus I times A3.
Oh, okay.
Yeah. That's what you
So
said.
A1, A2 equals minus I times A3.
Yeah.
Okay. Similar relations exist for all the other products. So what that shows you is the trace of any pair of products of these is
Zero.
0, which means they're orthogonal with respect to that inner product. In their length, like what's if you and then what if you take A1, what does that give you?
1. It should say identity.
I think
One,
yeah, the
zero,
identity,
zero,
right?
one.
So that actually gives you 1. So it's 2/2, which is 1. So his point next is you look at R3 and you make the correspondence with that and this V. So the correspondence explicitly would be what? Something like phi of xyz equals xa1 plus ya2 plus za3. You can look at R3 as a very particular type of 2x2 complex matrices, the so-called skew traceless traceless skew Hermitian matrices. Those are, so that's a 3 real dimensional vector subspace of FS, of 2 by 2 complex matrices. All right, now what? Suppose U is an element of SU2 and A is an element of V. So U an element of SU2, which is what again?
Complex matrices with orthogonal columns and determinant 1.
Right. Well, orthonormal
Orthonormal
is measured by the complex inner product. So I mean, it's a little bit. Anyway, it's this, right? I can be more specific.
Yeah.
I mean, here's just what you're saying, but with. I mean, this is
It's the same thing.
U conjugate transpose in another notation, right? All right. So he's like, okay, so you can multiply. You can conjugate, you can look at U, A, U inverse, right? So what we're saying A maps to U, A, U inverse, right?
Mm-hmm.
And so that's a mapping, this is, maps V to V, right? How do I know that? This has trace 0.
Yeah.
So, okay. And, oh, but we also need, what else do you need? It's not just that, you need that it's real. Like, what? Is it real? Why is he doing conjugation here? Sorry guys, I lost all of a sudden. Oh, I have this problem with stars and bars and daggers. I never know which one's which.
Mm-hmm.
That star is actually a conjugate transpose in my way of thinking.
Right. They don't use daggers in this book.
Yeah, I guess dagger is something I always make up, huh?
I
So
guess.
Because I was, as I've mentioned before, raised by physicists.
Yeah, the star is just the conjugate transpose.
Mm. So, for this, I mean, okay, the fact that that's traceless is part of it, but it should be traceless and traceless and conjugate. Like these are all equal to their conjugate
Right.
transpose. I said they were skew Hermitian. That's
They're
not
just
true. They're actually just Hermitian. So the set of traceless Hermitian matrices is 3 real dimensional. Then we can identify with our 3. 2 by 2 traceless Hermitian matrices. So the point was, if we take U, A, U inverse, and we dagger it, and that's equal to U inverse and dagger, A dagger, U dagger. But the thing about U dagger is U dagger
It's the inverse.
is U inverse, right? So this is really
U.
U dagger dagger, which is again, yeah, by the way, U dagger dagger is, sorry, it's making me too happy to say that. U dagger dagger is U again, so that's U, and A dagger is A, and that's U inverse, so there you have it, yeah. So indeed, that finishes the proof that this mapping, which I feel like I need to give a name, GU. So GU of A equals to U, A, U inverse, right. All right, what's next? For fixed U, the map A maps to U, A, U inverse is linear in A. Thus, for each U in SU2, we can define a linear map phi u of v to by the, oh, so you called it phi. I called it g. Oh, you can easily see that. And I guess phi is a better, fine. I'll use phi. It is, after all, he's about to do what?
Show it's a homomorphism.
Right. So phi of u1, u2 is equal to phi of u1 composed with phi of u2. You can see that from it's the sock shoes on the inverse, puts the 2 inside. So it does the 2 first, and then it does the 1 second. So that's this composition. And what else do we have? He also points out that it preserves the inner product, right? So like, we also have because that's going to conjugate by UU inverse and then another UU inverse. So the UU inverse interior cancels and the UU inverse exterior cancel by the symmetry property of the trace, right? Like this is trace of U inverse A, U inverse, rather, I did that backwards, UA, U inverse, UB, U inverse, which is the trace of AB, because these guys cancel by properties of the trace and the inside one goes to identity. Make sense? So what? Not sure yet. He says, once we identify R3 with the orthonormal basis, then we may think of phi u as an element of O3.
Since phi is orthogonal.
Ah. Oh, right, that's what this shows. This shows that. Is That's almost an explicit map. He still traded R3 for these matrices. Alright, fine. So, I think I can get rid of this right here. Yeah, I've got, okay, yeah, it should be fine. Yeah. I think I can make it explicit. Okay, so this map phi, right, so we have phi u is a mapping from what? It's a mapping from V to V, right? I want to trade that for a mapping from R3 to R3. I can do that with this phi map up here. Which direction does phi go at the moment?
R3, yeah.
So
We want phi composed with, or little phi composed with big phi u. With phi inverse.
that's a mapping from
R3, R3. Oh yeah. Oops.
it's okay. So then that's a mapping from R3 to V back to R3 again.
And it says R.
Right. These are isometries. They don't change the length. They see the vector xyz has the same as the same length as the vector xa1 plus ya2 plus za3 over there. So that this is an isometry, and so it follows then if I call this thing, say, gamma u or something, right? That we have. Let's see here, I'm going to say this. So you can prove that gamma u1, u2 is gamma u1, gamma u2, right? Mm-hmm. It's a homomorphism, and I think, well, u1 here. This is for u1, u2 in SU2, right? Mm. I'm trying to explicitly find what? I'm trying to find the covering map from SU2 to SO3. Yeah, I'm pretty sure this is it. I'm pretty sure what we do is phi of u is equal to the standard matrix of gamma of u. I believe this will be an element of SO3. It's definitely, I mean, I say SO3 are 3 by 3 matrices that are orthogonal and have determinant 1. I'm not entirely confident about the determinant 1 condition at the moment.
Yeah, I think he talks about it later.
But definitely it should be orthogonal because that forces the orthogonality condition. So we talked about a little bit later. Right. So there it is. That's the map I wanted you guys to find, I think. It's not quite as explicit as I would like still. I mean, it'd be nice to there is a slightly more explicit version of this thing. I remember it. So I can find it here real quick. I mean, like in this book, he sees, he's like, his formulas show him that the identity maps to the identity in SO3 and minus the identity in SU2 mapped to SO3. That's why this mapping is 2 to 1. Those two things both map to the identity. And I think here's the explicit mapping that he has in here. He takes u in SU2 equals to e to the I sigma vector dot theta over 2, and that maps to R equals to e to the I j dot theta. So these are the generators of SU2, those are the generators of SO3, and this is a shorthand for just a linear combination of the, you can almost see that, that's kind of what's going on here. This is analogous to the, this thing. That's the dot product of that and that. And anyway, I mean, I'm being a little bit heuristic here, but there are more formulas that are slightly more explicit than I'm showing you so far. But anyway, there it is, this corresponds. Okay, so anyway, there you have it. This is in fact a double cover. of SO3, that phi that I've just described over there, in fact, does give you a 2-to-1 homomorphism. How about UN? What's the covering group of UN? Tell you. I will tell you. Here you have G tilde. It's just kind of fun to look at these. So it's the reals direct product with SUN. And in this case, the covering homomorphism, I can actually write down and not be too snowed over by it. So you take theta and u, this guy and this guy, right? And so what do you think? Think about SL, like ON, you have determinant plus or minus 1, right? Whereas SON, determinant 1, right? Now in the complex case, SUN is just UN with the extra condition determinant 1. So, anyway, long story short, it is just e to the I theta times u. So this condition,
Can let the determinant be anything?
yeah,
Anything.
precisely, the determinant still has to, okay, so like,
It has modulus 1.
precise, yeah, the determinant, we're stuck with this, u dagger u, so that ends up being 1. So that says that the modulus of the determinant is, well, modulus squared, if you like, is 1. I don't know, number theory has forever ruined my terminology, but then there's stupid non-norm norms. But that says unit modulus. Of course, 1 is a special case of that. As we know, SUN is a subgroup of UN, but it's not all of it. But that, yeah, like you said, that frees it up. Take any determinant you like. And let's see here. The fact that this is simply connected follows from the fact that R is simply connected and SUN is simply connected. So the Cartesian product of simply connected things is once more simply connected. And you also need to show that the Lie algebras are isomorphic. But that's not hard to believe because like the Lie algebra of this is something like the Lie algebra of SUN. It's like one more dimensional than that, right? So it's kind of, I mean, sort of intuitively speaking, it's sort of like you've taken away, I mean, this has that determinant 1 condition which reduces the dimension by 1 from what it would be in UN, and that adds it back. And just in terms of sort of gross dimension counting, that's, but you can explicitly show, and it's probably a good exercise to prove that the Lie algebra of this is isomorphic to the Lie algebra of that. That's part of it. And now GSON is more interesting. This one I can't describe, although I might want to spend a whole other day with you guys if we have time to talk about this. I don't know. It kind of depends on where you guys would go and what I get energy to do. But the SON, its universal cover, is given by things called spin n. So spin n G tilde. I got to be careful with the capitalization. There's all kinds of punny notation that goes on here. But it's spin n. This is the double cover of the rotation group. Things that are assigned values in spin n are known as spinners. So like a spinner field is something where you're doing something like attaching a spin n thing to each point, something like that. As he mentions, this has connections with Clifford algebra, and he does maybe explain a little bit more of it later. Right. So anyway, those are just some universal covers for your amusement. Then we'll sit down. Let's see here. So then just kind of to tie it together here, because it's kind of, so again, if you look at G equal to SLN, I think we're talking about over the reals. I think it's the reals, yeah. Then the universal cover is not a matrix Lie group. For kicks, because I couldn't find it in here, I looked it up on the stack earlier. There's a fun answer to this question. Exactly what is the, just Scooter Rivers I meant. And so here's the answer. The universal cover of SON, it is, the universal cover of SLN is SON, Cartesian product with EK, where the second factor is some k-dimensional Euclidean space. In fact, the fundamental group is either Z2 for n greater than or equal to 3, or the fundamental group is just Z for n equals to 2. This implies that the universal cover is a two-sheeted cover for n greater than or equal to 3, and an infinite cyclic cover for n equals to 2. And then he answers the question, he's like, well, as for what kind of group it is, well, it's the universal cover of SLNR. And that's what it is. I mean, that's the thing, is calling it the universal cover characterizes what it is. It's the unique, simply connected group with isomorphic Lie algebra, and it has this connecting group homomorphism. You could come up with some point set which has these properties, but that's kind of beside the point. These are the properties which characterize it, so that's what you should think of it as. That was his answer. This is, I should give credit where credit is due. This is due to Neil. I love the stack, it's so much fun. Next section, the final section in chapter 3, is on subgroups and subalgebras, all right? And I'll just get to the point as quickly as I can. Basically, the point in this section is the following. It's the question that it asks at the start is really the thing that tells you what the section's about. He says, suppose G is a matrix Lie group, H is another matrix Lie group, and that H is a subset of G. Then certainly the Lie algebra H of frac H of H will be a subalgebra of the Lie algebra frac G of G. Does this go the other way around? All right. In other words, given a matrix Lie group, so I gotta erase some of this stuff. So here's the question. If you have H, right, is a sub, okay, so here's the observation. If H is a subgroup of G, and these are both Lie groups, right, then yes, frac H is a subalgebra subgroup. I usually use that for subgroup. Anyway, yes, the Lie algebra likewise behave, all right? So the question that is asked and answered in this section, partly answered, is if you have, G, the Lie algebra of G, and if you have H, a subalgebra of G, then does there exist H, a Lie group? Of course, here we're talking matrix. Does there exist a matrix Lie group such that H is a G and frac H is the Lie algebra of G, So if we have a sub-Lie group, then yes, we have a sub-Lie algebra. You can prove that by just differentiating, like, I suppose the inclusion map or something. Um, but this is trickier. And the reason it's trickier is this example he brings up right here. So for example, all right, if you have frac H, and what you can do is just look at IT 0, 0, ITA, or ITA, such that T is real, and A is irrational. This is a sub-Lie algebra, sub-Lie algebra of frac G for G equals to, let's see here, just GL2C. Remember GL2C, this has, what's the Lie algebra for GL2C? It's not that hard, it's just little GL2C. It's just 2 by 2 complex matrices without any kind of strings attached. That's the total general linear group. 2 by 2 complex matrices. But this, of course, is a, can you add these? Get the same thing back again, yes. If you take the product of those, you get something of the same type because you multiply diagonals. And if you multiply products in reverse orders and subtract them, that's the commutator, still the same thing. So it's closed under commutation. This is a subalgebra with respect to the commutator bracket. All right. And the thing is, if there was an H, would contain what? It would contain H naught, which is formed from something like exponentials of these things, right? In particular, if you exponentiate something like this, you just get e to the it, because the exponential of the diagonal is the matrix is the diagonal of the exponentials. Right. So, and that for this to be, it would have to contain that. The Lie group would have to contain that, because it has to contain whatever the matrix exponential goes to, right? That's at least inside the Lie group, if not more. And the thing about that is, yeah, well, the closure of this, as he points out here, by exercise 1 of chapter 1, which you guys should do, the closure gives you this. Just I mean, that's the closure. It the point is that keeps going and going and going and going and going and going. So if that being irrational means that as it goes on, if you think about the unit circle here, it's hitting everything in the unit circle. All irrational points in the unit circle, it's hitting all of them as time goes on. And so the completion of that just fills it in and gets all real values in that second copy. And the first copy was already there, so it's still there. But then this closure has 2 real parameters. This is a 2-dimensional Lie group. It would have a 2-dimensional Lie algebra. Oopsie, because this is a 1-dimensional Lie algebra. That's a problem, because this necessarily is in, And so what he describes here is how we can, so basically the game that's played here is that, you can look at it philosophically a couple different ways. The one way you can philosophically look at it is our definition of Lie subgroup was dumb. Because surely this correspondence should work in the proper set of definitions. It's one way you could look at it. The other way you could look at it is our definition was fine. but we just need a new definition. We need some weaker notion of what's a subgroup. That's what he does here. He says, if H is any, his definition, if H is any subgroup, notice not Lie subgroup, but just matrix, like a group theoretic subgroup. If H is any subgroup of GLNC, define the Lie algebra H of H to be the set of all matrices such that E to the Tx is an H for all real T. So he's like, okay, so if G is a subset, excuse me, if H is a subset of G, and this is a group. All right, I'm not saying it's a matrix Lie group. I'm not that business about what's the quick way of saying it? Non-singular limits. How's it go?
It's either closed or not in GLN.
Closed or not in GLN. Thank you. Very good. So none of that. Just it's a group.
It's just there.
Then the Lie algebra of such a thing, which is, by the way, not necessarily a matrix Lie group, is elements of form E to the Tx, x rather, such that what? X is the thing in there, such that this is an element of H. For all of T in the real. It's a sneaky definition again. He's like, X is in the Lie algebra. If when you exponentiate it, it lands back in the group. And of course that makes sense because this is the matrix exponential, which we can have our way with and calculate willy-nilly and all that. So, with that definition, he then makes another definition, connected Lie subgroup. And a connected Lie subgroup has a couple of conditions. Number one, it's a subgroup of G. All right. Number two, the Lie algebra H is a subspace of frac G, so it has a natural Lie algebra. And number three, every element in H can be written as a product of exponentials of the Lie algebra of H. So connected. Glad we figured this out. This has been bothering me. I feel almost better. I'll feel better. I'm not going to feel really better until I explicitly write down a formula from one to the other. We are much closer to doing that. This thing I just wrote down here was the formula. I just need to understand it again. It's been a few years since I properly understood it. Oh well. So, again, definition, connected Lie subgroup. Three conditions. One, H subgroup of G in the usual way. Two, and this is for G matrix Lie group, okay? Two, the Lie algebra is a subspace of G. So here, H, Lie algebra of H in the newly extended sense. Like this business over here we just did, right? You don't have to pen, it's fine. It should be obvious. And then three, each element of H has form e to the x1, e to the x2, e to the xm for some x1, x2, xm in the Lie algebra. These are also sometimes called analytic subgroups. Theorem, proposition, he says, if G is a matrix Lie group and H is a connected Lie subgroup, then H is path connected. Any two paths can be, so like this definition, so connected Lie subgroup implies path connectedness. That's a nice little proposition, and as he says, that kind of explains the name a little bit, right? Next proposition here, if G is a matrix Lie group with Lie algebra G and H is a connected Lie subgroup, then the Lie algebra H of H is a subalgebra of G. Now I said sub, I should be clear, this is just subspace. So his next proposition is, hey, not just subspace. Get brackets for free. Whee! So in other words, H is a subalgebra of G. I don't know what my notation is. If this is subspace, then we also have that, like the bracket of H is equal to the bracket of G restricted to H cross H, okay? Basically, that's a subalgebra. Same bracket, smaller domain, okay? And a subspace, so that's a sub-Lie algebra. So that's proposition 3.14, which the proof of, I like the look of, but we must move along. But it's actually got differentiation in it, and that makes me happy. But anyway, I should. And it's also got that same topologically closed argument that we never quite understood. Or we understood, and I didn't understand. Theorem 3.15, let G be matrix Lie group with Lie algebra G, H is Lie subalgebra of G, then there exists a unique connected Lie subgroup H of G such that the Lie algebra of H is H. The subgroup H consists precisely of the elements that are formed by the product of finitely many exponentials of the sub-Lie algebra. Aha, so there exists a unique connected Lie subgroup. All right, that's nice. Proposition 3.16, I will not read. The ultimate point here, guys, is just this. And this is really the theorem that this is all leading up to. The one that's worth remembering with suitable fine print. Theorem 3.118. It's this. Every finite dimensional real Lie algebra is isomorphic to the Lie algebra of some Lie group. So there you go. We have now created suitable concepts, weakened notions of subgroup as to permit this theorem. The thing was, this example, the insistence that matrix Lie groups have this rather greedy, structure of a matrix Lie group that was too strong. We have to allow for more exotic subgroups. And once we allow for that, then there's enough room to make this happen. And he also has this theorem 3.17, which is probably important to understand. Suppose G is a matrix Lie group and H is a connected Lie subgroup of G. H can be given the structure of a Lie group in such a way that the inclusion of H into G